In the last subsection, we introduced the concept of expected values. And in particular, we looked at one expected value that looked at how far off the random variable was from its overall mean. Now, in this section, we're going to look at another measure just like that that's more often used as a way to measure how much variability there is in a particular population. And this particular measure that we're going to look at, or this particular expected value, has a special name. It's called the variance. We've already seen the variance before in terms of a sample and a little bit in terms of a population. But now that we have a PDF, a probability distribution function to work with, now we have a convenient way to find then the expected value relative to this measure of variability, which we're going to call the variance. Okay, so this is what the expected value looks like. It's the expected value of the quantity y minus mu squared. Now, again, what we've seen in the past was that sigma squared was the sum over all possible values of y minus mu squared divided by the population size. But now, since we have a PDF that quantifies how items are distributed in the population itself, like how often we have, let's say, a GPA between 3.5 and 4, now we have a way that we can basically find this same variance with respect to this probability distribution function. Okay, so let's say that I have a discrete random variable y, and I'm interested in this variance, which we will again call sigma squared. That's going to be equal to the expected value of how far y is off from mu, that quantity squared. With a discrete random variable, that means let's sum over all the possible values of y, and we're going to take y minus mu squared, just like how we had here. But now, rather than weighting it by 1 over n, we're going to weight it by the corresponding probability of getting a particular value of y. That's when y is discrete. Now, when y has a continuous distribution with it, then we replace again the sum with an integral, and we change what f of y represents a little bit. So that's the variance. With the variance, we can also talk about the standard deviation, and all that is the positive square root of the standard of the variance itself. Very often, we will prefer to work with the standard deviation instead, because if we look at the variance, notice we have a square term there. So what this is giving us is quantities that are in squared units, like maybe $ squared or GPA squared. I don't know what that means, but that's what a variance would be in that particular situation. So if we take the square root instead, then that means that we can now work with the original units, like dollars or GPA. Okay. So again, all that a variance is a measurement of how far you would expect y to be from mu squared. The reason why, or I guess we should also talk about this, the reason why we use a square there is so that we always have a positive value. Similar to what we saw with an absolute value with that expectation before. But this measure of variability is much more widely used than working with that absolute value. So this expected value of y minus mu squared, notice that's just a special case of working with some function of y, that's g of y that we saw in the previous subsection. Also, remember what mu is. Mu itself is an expected value. It's expected value of y. So one could rewrite the quantity such as this. So you essentially have an expected value with an expected value. That gets a little bit kind of confusing, so that's why people often just usually put a mu there instead. Again, multiple notations to mean the same thing. Unfortunately, you just have to get used to it because this is these different terms, these different notations used widely outside of this class. And so So anyway, so you could write it so that you have the expected value there in sight. But remember what that expected value is. Essentially, it's a constant. Once you find that expected value, like 30 in our transaction type example, that's what it is. A 30 is a 30. If you take an expected value of 30, it's 30. So notation. So sigma squared is our variance. Some people will denote it as sigma squared y, where that y is there to emphasize that, hey, we are dealing with a particular random variable y. If our random variable was x instead, people would denote it as, let's say, sigma squared with a subscript x. Another common notation, I use this a lot, is rather than saying e parentheses m parentheses, instead they use var for variance, var of y. That's what I often like to use myself, and you'll see that throughout. Now, since we're working with squared units here, if I take y squared, of course, that has to be positive. If I take y minus mu squared, that has to be positive. So that means sigma squared is always greater than or equal to 0. And since sigma is the standard deviation, is the positive square root of the variance, of course, sigma is always greater than or equal to 0 as well. Now, there's a nice little, you could say, shortcut way to calculate this variance. And that is, our variance can be rewritten as this. The expected value of y squared minus the expected value of y, that whole quantity squared. And again, that expected value of y there would be just mu. So why do we have this expression, or this alternative way to find the variance? Why are they equivalent? Well, let's do a simple proof. So here's our expected value of y minus mu squared. Then, if I just simply multiply the stuff out that's inside that expected value, so take y minus mu squared, actually multiply it out. We get y squared minus 2 times y mu plus mu squared. Now, earlier, or a previous subsection, we learned this. If I had constants a and b, the random variable y, I can find the expected value. Actually, I think we did this instead. Expected value of a times y plus b. This is equivalent to the expected value of y plus b. We can use the same idea here to further simplify our expression. So what we can do is simply always move this expectation inside of a sum, or if you're subtracting. So I can move this expectation inside of this sum or subtracting there. And I'm left with the expected value of y squared minus 2 times mu times expected value of y. Y as in why. Well, remember how we found the expected value of a times y is a times expected value of y. If that's not clear, go back to our previous discussion about that when we were actually writing everything out in terms of integrals. And we have expected value of mu squared. So in let's say a step number 3 here, we have the expected value of y squared again. And the expected value of y, of course, is just mu. So I have mu times mu, or in other words, mu squared. I got 2 of them, because I have that 2 out in front. And then the expected value of mu squared itself here. Remember, mu is an expected value, so it's going to be a constant. Like with the transaction type example, expected value of y there was 30 seconds. Well, what's then the expected value of 30 seconds? Well, it's 30. What's the expected value of 30 seconds squared? Well, it's 30 seconds squared. And so because of that, that expected value that was out in front simply disappears. So I have a 2 mu squared, and I have a mu squared there. Notice I have a minus, I have a plus. So if I subtract, I get minus mu squared in the end. And so this then results in this nice little, you could say, little shortcut formula. In terms of actually doing calculations, this is what's more often used because if you already calculate expected value of y, if you already calculate expected value of y squared, then you got the corresponding quantity. Also, doing the integration in terms of actually, let's say, doing the integral of y minus mu squared times f of y dy, that's going to be a little bit more complicated than what it really needs to be. And so if you can simplify it into two different steps there, it can greatly simplify your life. Okay. Perhaps that's a little bit longer explanation than what was needed, but hopefully that's clear. If not, please let me know. So let's talk about how we can do these calculations now. We're going to go back to our Plinko example that we saw before. So here are the corresponding probability distribution functions. We've calculated the expected value of your winnings, expected value of x. Here's the corresponding standard deviation, or sigma itself. And we can see from these values that there's a lot of variability in terms of how much you could win. And if you remember before, when we were discussing means and standard deviations with respect to a sample, we use this rule of thumb for the number of standard deviations all data lies from its mean. Well, the same thing that can be used here. Now, though, this is, let's say, with respect to the population itself. Where would you expect, in this particular case, all possible winnings to lie for someone who's actually playing the game? And so if I take mu minus 2 times sigma, mu plus 2 times sigma, and this is what I get. So, for example, if I were to drop the chip right in the middle of the board, I would expect winnings of between negative 5,500 and positive 11,000. Now, with this rule of thumb, when you have a discrete random variable, and there's only a limited number of possibilities here, the results of these bounds here might not necessarily make sense. But the main thing to understand from this is that there's a lot of variability. It would not be unusual to get 10,000. It would not be unusual to get a very small amount as well. So let's take a look at, in particular, if I were to drop it on the side of the board where there's a $100 slot, how would I actually calculate then the variance? And we'll use the longer formula for this. So I want to find the expected value of x minus mu squared. In other words, I want to take the sum of over all possible values of x, 100, 500, 1,000, 0, 10,000. I want to each time find your winnings minus the mean winnings, square it, and then weight it by the corresponding probability that you get those winnings. So, what's the probability that you get 100? 0.1667. So I take 100 minus 850, which was the mean that we've calculated before. I square it times the corresponding probability. Now for 500, I take 500 minus the mean, 850, square it, weight it by the corresponding probability. I do that throughout for all possible winnings, sum them up, and I get $3,237,500 squared. On the surface, this looks like a lot, but again, it's dollars squared. So if we put this in the original units that we would be working with, which is this dollars, take the positive square root, we get 1,799. And then that makes sense to us, or at least more sense to us than that dollars squared. Now, let's talk about how we can do these calculations in R. So what I could do is simply create a vector that has all my possible values of my random variable, 100, 500, 1,000, 0, 1,000. Then create a vector that has all the corresponding probabilities. And then, how about we take each of the x's times its corresponding probability. And the way that R operates, and we've seen this before, what it's going to do is an element by element multiplication. So it's going to take 100 times 0.0176. It's going to take 10,000 times 0.2471, and so on. And so now I'm going to have a vector of these 5 different products. If I sum all those potential values up, I get the mean, 2,752. And I'm sorry, I failed to mention this before. This is for now the $10,000 slot, meaning you're dropping it right in the middle of the board. Now, to find then the variance, sigma squared, I do exactly the same kind of thing. I take all my x's, I subtract off the mean for each of them, and it's going to do this element by element. I square it, weight it by the corresponding probability, and then I sum all these items up, and I get the variance as what we see. Well, I guess it's not in the table itself, but the variance is there. And then the corresponding standard deviation, which is in the table, 4,170 by taking the positive square root. Now, if you're not comfortable, oops, let me actually do some erasing here. If you're not comfortable with some of this discussion, now that we've been using R for a while, what I recommend that you do, rather than me walking through it myself, is that you go through parts of the calculation. So look at x times the fx 1000, which represents that PDF. Run that code, look at the results, and you're going to see it's an element by element multiplication. Take a look at x minus mu. Just run that segment of code alone, and you're going to see it's element by element subtraction. Then run x minus mu squared. See that it's element by element squaring. Do that throughout so that eventually once we get to the sum, you say, okay, that's how that comes about. Of course, though, if you do have questions, you need to ask. Now, when we're doing these calculations, obviously we can do them in R. Sometimes, especially since there's a small number of values of x here, sometimes it's just easier to just go to a spreadsheet and do it. And so if you want to see this, I just simply wrote this all up in Excel, how all these calculations would actually be done. Okay, let's move on now to the transaction time example. Again, x is our continuous random variable that we're working with, and we'd like to be able to find now the variance for x. So in other words, we want to find sigma squared, otherwise known as var of x, otherwise known as the expected value of x minus mu squared. In other words, the expected value of the squared deviation from the mean. How do we find this? Well, we take the integral from 0 to infinity of x minus mu squared times the PDF, integrate with respect to x. But remember here, mu is equal to 30, so I could actually plug that in there. Now, if you were to do the integral there, what you would need to do is simply you're going to have to multiply out all the terms that's inside the x minus mu squared, do a few integrals, and do that. Instead, though, what would be easier is that, well, we've already found mu to be 30 before, so let's just square that. And we've actually calculated the expected value of x squared before as well, and that was 1800. So if we take 1800 minus 30 squared, I get 900. That's my variance. How would we do this in R? Let me actually come on over here to R. So I need to create an R function of what we're trying to integrate. So in this case, it's x minus mu squared times our f of x that we've had before. This function is going to be called pdf.var for the lack of a better name. Now notice in this particular function, I have an x and I have a mu. So I'm going to have to pass in the value of mu into it as well, similar to what we saw with finding the expected value of the absolute value of x minus 30. So to do this integration, I use the integrate function. My f argument is what R function I'm trying to integrate, my lower bound, my upper bound, and what my value of mu is. And let's go ahead and run that. And I get 900. Now notice what this error is here, 0.022. This is a little bit larger than I would normally be comfortable with. So if we want to, we can change the argument rel.tol to be more precise to make sure that we got the right answer. And when I do that, we can see my error is very small, and I ended up with exactly the same answer. Of course, in R2, you could do the calculation like this. Take the integral of x squared times f of x. It's above in my program. Here we go. pdf.xsq is now x squared times the f of x. I'm going to now immediately take out the corresponding value that's calculated by the integrate function, and then I'm going to subtract off what we've calculated before as mu, which was saved in an object, and square it. Oops. Let me do that again. Okay, I haven't run parts of this code yet. That's why that happened. So let me go ahead and do that. And there we go. We get 900. Let me get back into my notes. If I were to do this in Sage, well, again, you would do what you would expect. Put in x minus 30, caret sign 2. The caret sign means squared in Sage's syntax. Multiply it by f of x. I'm integrating over x. I'm integrating from 0 to infinity, and you get what you need. Okay. Now now one thing I want to mention. So of course, then the standard deviation is 30. It's the positive square root of 900, and it just so happens in this case the mean is equal to the standard deviation. For probability distribution functions in general, that won't happen. It just happens in this particular case. This is because this particular PDF that we're looking at is what's called an exponential PDF, which we will spend some time later on the semester exploring in more details about why that happens. Now, let's think about that rule of thumb again now with respect to this transaction time example. If I were to take mu minus 2 times the standard deviation, I would get negative 30. Mu plus 2 times the standard deviation, I get 90. And so what that says is I would expect all transaction times, almost all of them, to be between negative 30 and 90. Of course, you can't have a negative value, so think of it as 0 to 90. If I were to do 3 standard deviations, I get from negative 60 to 120. And so let's go back to our plot of the probability distribution function. And again, that says between 0 and 90, or if you want to go up to 3 standard deviations, 0 and 120. And so that we can see that indeed most of the area underneath the curve is between these 2 points that we get from our rule of thumb. And so that helps illustrate again what this standard deviation is actually measuring. It measures how much variability you have in your population. And so in this particular example, just for emphasis, we see that pretty much all observations in terms of the proportion of all observations in the population, which this particular PDF is trying to characterize, almost all observations will be between about 0 and 90 or 0 and 120. Now, we could compare then sigma also to what we found earlier for that expected value of the absolute value of x minus mu. And we can see they are somewhat similar. They're not exactly the same. We shouldn't expect them to be. They're just 2 different measures of variability. Again, though, generally most people focus on a standard deviation. Let's look at some other parts to this example to help you understand what the standard deviation measures. Let's suppose we change our PDF to this. It's exactly what we had before, but instead of having a 30 in there, we have a 15 instead. What one can show, and you should be able to do this on your own, is that the expected value of x, or mu, is equal to 15. The variance is 225. That standard deviation is 15. Here's a plot of the PDF with the 15 in there. That's what's represented in blue. But I also put the plot that we've had before when I use a 30 instead. I put that in red. And what we can see here is that when I have that PDF that uses a 30 instead, you're more likely to have things more spread out in terms of look at the area underneath the curve. It's not unusual to have some values of x down there, but it would be unusual for the PDF that has the 15 in there instead, which is represented in blue. And so when we had the red PDF, we had a sigma equal 30. When we had the blue PDF, we had a sigma equal 15. 30 is greater than 15. So think about what that means. Again, the standard deviation is measuring how much things are spread out in the population in terms of the numerical values. The larger the value is, the more variability is, the more dispersed, the more spread out these values are in terms of their numerical values. Okay. Now, we focus on, in this particular section, a case where g of x, some kind of function of x, was x minus mu squared. But there are also other cases that one could look at for other functions of x, if that's your random variable, or other functions of y, if that's your random variable. And one of these measures is something similar to what we discussed before called the skewness. And what the skewness is defined as is as follows. For that g of y, we use y minus mu cubed, find the expected value of it, and then we divide by sigma squared raised to the 3 divided by 2 power. That's called the skewness. Okay? Now, similar to what we've seen before, values of skewness, well, we've talked about skewness like with respect to a histogram, right skewed, left skewed, and so on. Also symmetric. So now relating that to PDFs, here what we have is a perfectly symmetric PDF. This would have a skewness of 0. Instead, though, if I had a PDF that looked like this, similar to what we've been working with the transaction time example, that skewness would be positive. Turn that around or flip it around, you could have a negative skewness as well. Now, there's another measure that we could look at. So for that g of y value, we could put y minus mu to the 4th and find the expected value of that. And then if we divide by sigma to the 4th, we get a measure called the kurtosis of a random variable. And here's a very crude diagram to help illustrate what kurtosis means. It corresponds to how peaked the probability distribution is. In other words, notice that the red probability distribution that I crudely drawn there has a more higher peak to it than the blue, and so its kurtosis would be larger. I have to admit that kurtosis is not necessarily as important as, let's say, the skewness, but something that you will hear sometimes talked about. And lastly here, we could also look at variances for functions of random variables as well. So I could look at the variance, or var, of g of y. Some people will denote this as sigma squared and then the subscript g of y there. And all that is just another expected value. The expected value of g of y minus its corresponding mean, in other words, expected value of g of y. That quantity squared, and then we take the expected value of all that. In terms of discrete random variables, we sum over all possible values of y, my g of y minus the mu sub g of y squared, weighted by its corresponding probability. That's for a discrete random variable. For a continuous random variable, we make the same kind of substitutions as we've done in the past. So with that then that concludes in this section on the variance of a random variable.